entry that we need to do, and off we go. Which means that we need an exact match on the destination IP. You know, we have the full IP that comes in, and we look it up in some form of map, some form of hash map. Okay, great. Off we go, send out this packet. Order 1 lookup, perfect. Other than, well, we have 2 to the 32 IPv4 addresses, we have 2 to the 128 IPv6 addresses. I'm not even going to try and figure out how to say the numbers, the IPv6 number, but they're big numbers, right? We would have to have a really, really large forwarding table with all these entries in to be able to do these exact matches. Equally, we have to figure out updating these tables and keeping them current. The larger table, you know, these large tables are a lot of work to be able to keep current. And it sort of ignores a fundamental thing about IP addresses, which is the hierarchical. When I want to start a network, let's say I'm Google, I go to some internet registry, that's the people that assign IP addresses, and they say to me, hey Google, here's a big block of IP addresses. You go and figure out what you're going to do internally, we don't care. But here's your block. So give me an IP prefix of some size. And then internally I assign it, like maybe I go to the guys in search and I say, oh, okay, this is your IP. This is your prefix, your IP prefix. I go to the guys in YouTube and I say something similar, and we kind of divide it down like that. But from everybody else's perspective, they don't care that I assign to search or to YouTube. They care that these need to go to Google. And Google can figure out where it should send the packets itself. So there is this kind of inherent hierarchy to the way that we have IP addresses. And practically, on the internet, we don't use any smaller blocks than 256 addresses. You cannot go and announce a smaller block than 256, a /24 prefix, to another internet network. It just won't listen to you. It'll filter it. Internally to networks, we do have to think about it, though, because you might have an IP address that is just one IP address, a /32 prefix, that we have to care about. But in general, we can think about how to exploit this hierarchy to give us more compact tables at the expense of lookup complexity. We can't just do this single lookup on the exact destination IP address now. We have to think about how can we look up something more than that. So, what does that work? What does that mean? It means that we have to try and find the IP prefix that matches the packet that we're trying to route, trying to forward. So let's look at this example. We've got Verizon. They are connected to AT&T. AT&T's got a bunch of downstream customers. We've got a packet here that's going to ABXY. So in that scenario, we're saying, okay, the destination of the packet is ABXY, and we want to go and look. Each network has to look in its forwarding table to say, well, where should I send that? And what it's trying to find is the prefix that matches that address. So Verizon here has A/8, then says, well, I don't know anything other than that should go to AT&T. AT&T then has inside, it says, well, I own A/8. But actually, internally to my routing table, I know that UCSF should have AD, LBL should have AB, and UCB should have AC. So in this case, AT&T does some lookup, and it says, well, what prefix in my routing table matches? In this case, it's something that starts AB. A /16 means that the first 2 octets of this address are fixed, so it knows that it needs to send it to the LBL next hop. So that's all very nice when there's just one route. But in practice, we have, in the internet, we don't just connect with one person and have this kind of tree structure. We have a mesh of different networks. All the networks interconnect to each other differently and can interconnect with each other in much more meshy fashion. So let's think about a simple case of that where here we have LBL that decides it wants to connect directly to Verizon. So Verizon now has routes that it's got this A/8 route that says, well, everything in it that starts with A, that should go to AT&T. AT&T's still got the same table. It's still got all those individual networks knowing where the downstream bits of the subdivisions of that prefix are. But now Verizon also knows that LBL has got AB/16. So it knows that anything that starts AB, those first 2 octets are fixed, should go to LBL. So in that scenario, well, we actually need to know not just what prefix matches, but what's the longest prefix that matches, so that we can send the packet to the right network. And this is longest prefix match. So essentially it says, take the most specific route that matches the destination of this packet. If it addresses multiple, if the address matches multiple prefixes, take the longest, the most specific. If it doesn't match anything, then we have a default route. So that's the route that says, well, if we don't know anywhere else, we'll just send it to this other next hop that might be able to do it. In some cases, we might not have a default route. If we don't have any route for the packet, we just drop it. We don't know where it's going. So LPM is the mechanism that gives us the way to do those lookups. So we'll spend a bit of time stepping through a few examples. So let's think about this pretty simple network here, where we have 4 different ports. Each one of them's got a prefix. They don't overlap. So P1 here has got the 201.143.0.0/22, and so on through the other ports. You can see there's individual ports mapped to each prefix, 1 per port. And so we want to find a matching route. So we have this packet that comes in. It's going to 201.143.7.210. And we want to figure out, well, where should that go? What port do we put that out of? That's the lookup mechanism that we're trying to do. So how do we do that? What we will do to start with is we start by converting the addresses to binary. Rather than thinking about this as 201.143, we'll think about it as 110, blah, 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 blah. So, and then we do the same thing in the routing table. And in the routing table, we have some concept here of wildcards, bits that aren't fixed. So you can see here where the hyphens are, where the horizontal lines are in the address. Well, our /22 has the first 22 bits set, but the rest of them are wildcard. That's what we said. The prefix means that prefix is this many bits are fixed and everything else is variable. So we convert the routing table into that form where now each one of these entries has the full specification in binary of what the mask that we should look at is. And if we kind of ignore the first set of parts of this address because at least the first 2 octets are completely fixed, and even the first half of the third one is fixed, and we think about these 3 bits, then what we start to do is we look at each bit as we go along. And we say, here, okay, we've got a 1. So look through our table and say, well, what matches here? Well, this one doesn't because there's a 0 in this bit position. But the remaining 3 do. They all match they all match the 1 here. So then we move on to the next bit. We say, okay, there's a 1 there. Now in this scenario, we look again, we say, oh, well, we look through these prefixes and we say, well, this next one, this top one's got a 0 here, but we wanted a 1. So that's not the same prefix. Again, we look at the next one, something similar, we can say. There's a 0 there. But this last one has a 1 here, i.e. we match this, and it's got a wildcard afterwards, so we know anything is going to match. So in a naive implementation here, we could say, let's check the incoming address in binary against every prefix that's in the table, and select the longest one that it matches with. But note this isn't check the address against all prefixes and find the one it matches the most bits with. We really care that it's got a fixed bit string, the prefix matches, not just that these 2 prefixes have most in common. So we need to do this bit by bit comparison. And there we go. So now we want to do that lookup, but it's kind of easy when we had 4 prefixes, right? We could just step through each of them. The lookup is on the order of is on average the order of the number of entries. But the IPv4 internet is about 1 million prefixes. So every time we get a packet and do a lookup, we would have to look through, on average, 1 million different entries. Scales really poorly. So what we want to look at is how might we use the structure of addresses to be able to improve the efficiency of that lookup. And so we can leverage the fact that there's a tree structure of binary strings. So here we can see we've got every one of these addresses that we were talking about before converted into a binary string, and a mapping of them. And we'll just really think about these 3 bits in the middle, because I think if I spend the morning reading out binary strings, it's probably going to be tricky to follow. So let's think about these 3 bits, the blue ones here and the orange ones here, and the mappings that they go to ports. So we'll look here that this is just those 3 bits pulled out. We'll focus on where the differences are in the addresses. That's why we're throwing away the rest of them. And so we have 4 different entries. We have one that starts with 0 and then 2 wildcards. We have a 100, a 101, and a 11, and then a wildcard. So I switched to using an asterisk for the wildcard here. And what we can do is we can take those and we can draw those into a binary tree. So we can start out with nothing and then say, well, if the first digit is a 0, take the left-hand branch. If the first digit is a 1, take the right-hand one. And go through these 3 bits and draw the binary tree that describes them all. Then at each point in the tree that we have a forwarding action that we associate with it, we can attach that to that node in the tree. So here you can see this orange node up here. That's where we said, well, it matched a 0, and then there were 2 wildcards. On the right-hand side, well, we didn't have anything that said it was a 1 and matched if there was a 1, then wildcard. We didn't have an entry there, so don't have anything. On the rightmost branch on the 1, well, we did have something that said there was 1, 1, and then a wildcard. So we attached the port 4 action there. And then down on the other branch, we have, well, it was a 0, and then we have exact matches for the 3 bits, the 3 bits there. So we have 2, right at the leaves of the tree, we have 2 forwarding actions that we installed. So that kind of looks like this. If we ignore the bits that didn't have any actions attached to them, then this is what we end up with. We end up with this tree that's got, at different points in it, it's got the forwarding actions that we're going to take there. So now we want to do a prefix match in that tree. So we were saying before that we're going to step through the bits and do a comparison. So here we say, okay, this is 1, 1, 1. So now we walk down the tree from the top. We start say, okay, it matches everything. It's got a 1 as the first digit. Then next digit is a 1. And now we've got a wildcard. So this matches this case. So this 1, 1, 1 would go out port 4. So that's and if we were to take something similar in for other scenarios, we would, if there were different bits here, we would walk the right branches of the tree. If it just had anything starting with 0, we would find that port 1 matched that exactly. Then for 100 or 101, we would have exact matches for those. So we can walk down the tree and compare the bits that we're looking at against the actions that we should take. But let's think about this multi-homing case, where we had this network that decided to connect to both Verizon and AT&T. So we didn't just have these, individual actions in the tree. We had ones that potentially overlapped. So our mechanism of walking down the tree and just finding the action that, that exactly matches, that might not be the right one. So let's look at what changes we might make. Because in this case, we've got some prefixes that overlap. If we think about the Verizon case, I'm not going to think about exactly the case. We're just going to add something to our 3-bit example here, keep things simple. And so here we've got port 1 that has got 0, wildcard, wildcard, and port 5 that's got 0, 0, 1. See, those 2 overlap with each other. So let's think about how we might represent that in the tree. And so what we end up with is just taking the same approach, putting these things in a binary tree, and then going and adding these forwarding actions still in the tree as they were where they were. But rather than having just one thing in this branch now, one on the left-hand branch, we've got now overlapping entries. We've got 2 entries that could be matched. On the right-hand side, we don't have that overlapping, so we've got the same approach as we had before. So now when we go and look at that packet, we go and take the comparison. We still walk down the tree, and we say, okay, it's a 0. Next time, we also hit a 0, so we match that port 1 action. Then we say, okay, well, let's compare the third one. It's a 1. Okay, we found the port 5 action. So for this exact match, we know, okay, we should forward out of port 5. What happens when we get 0, 0, 0? We walk down the tree. We say, okay, there's a 0 here. Let's go to port 1. To that 0 wildcard. It's going to be port 1. We hit a 0, and then we find a node that's got no action associated with it. So, well, in our previous model, if we just look up the exact thing, then we're going to end up in a scenario where we don't know where to forward this packet. So actually, we need to tweak our design a little bit. We need to say, rather than walking down the tree and finding the exact match, walk down the tree, remember the last action that you found, and then if you reach a stage where you don't find an action in that hop, but you match the packet, then use the last action that you remembered. And so that gives you then a way to say, well, in the scenario that you have an exact match, you overwrite the last action when you find the exact match. And when you don't, you just use the action that you previously found. So if we look here, then we would have said, okay, we hit port 1 with 0, 0, 0. We remember port 1. We hit the 0, 0 wildcard. We say, oh, there's not a match here. But that's okay, because we already found port 1. But differently on the right-hand side of the street, if we take the same thing, if we got to the